a tiny creature from 500 million years ago, is rewriting the story of life's biggest group, arthropods. Imagine a sea floor in ancient Yunnan, China, where a minuscule organism with stalked eyes and grasping arms scuttled through the sediment. Its brain, barely larger than a pencil tip, holds secrets that could upend decades of evolutionary theory. But here's where it gets controversial. This fossil, Jianfengia multisegmentalis, isn't just another relic of the past. It's a time machine that forces us to rethink how insects, spiders, and crustaceans came to dominate Earth. And this is the part most people miss. The answer lies not in its claws or legs, but in the neural architecture buried within its fossilized remains. Arthropods, those jointed leg wonders we see today, include insects, crabs, spiders, and even centipedes. They're everywhere, crawling on your walls, skittering under rocks, or lurking in the ocean depths. Their success? A mix of exoskeletons, segmented bodies, and limbs that have adapted to nearly every environment on the planet. Yet one mystery has nagged scientists for years. How did this vast group split into two major branches, mandibulates, think ants and crabs, and chelicerates, spiders and scorpions? Until now, the answer was a fog of uncertainty. Enter Jianfengia. Initially thought to belong to a group called megachirons, creatures with claw-like limbs, researchers placed it among chelicerates. But a closer look at its brain told a different tale. A team from the University of Arizona reconstructed the fossil's nervous system using 4 exceptionally preserved specimens. What they found shocked them. A brain structure eerily similar to modern shrimp and crayfish. Even the cone cells in its compound eyes mirrored those of living crustaceans. This wasn't a distant cousin of spiders. It was an ancestor of insects and crustaceans. So, what's the big deal? Let's break it down. Mandibulates have antennae and jaws, while chelicerates rely on fangs or pincers. Jianfengia lacked antennae but had sturdy head appendages used for grasping, features that evolution later repurposed into antennae. Meanwhile, its chelicerate cousin, Evolutionary, had a brain resembling today's horseshoe crabs. Despite their similar exteriors, their brains revealed divergent evolutionary paths. One led to crabs and beetles, the other to spiders and scorpions. This discovery challenges a long-held assumption that physical traits alone define evolutionary relationships. As lead researcher Nicholas Strausfeld notes, soft tissues like brains rarely fossilize, but here the conditions were perfect. The fine-grained sediment of the ancient seabed preserved neural details scientists never thought possible. Co-author David Andrew adds, the brain structure aligns with living arthropods, proving their evolutionary blueprint is both ancient and remarkably stable. But here's the twist. If brains can rewrite evolutionary history, what else have we missed? Could other fossils hiding in museum drawers hold similar surprises? And what does this mean for the future of paleontology? Frank Hirth, a co-author from King's College London, suggests this robust neural architecture explains arthropods' dominance. Their brains evolved once, then diversified, giving them an edge over competitors, he says. Still, questions linger. Did Jianfengia truly bridge the gap between ancient and modern arthropods, or is this just one piece of a larger puzzle? And if its claws evolved into antennae, what about other traits we've misclassified? We invite you to weigh in. Do you think this fossil is the missing link, or is it just the beginning of a deeper mystery? Share your thoughts below. We'd love to hear your perspective on how evolution shapes life's grand family tree. The full study, published in Nature Communications, is a reminder that even the tiniest fossils can hold universe-sized secrets. So next time you see a spider or a crab, remember, their story began with a brain no bigger than a pinhead, scuttling through an ancient sea.